you all. Now our guest is available with us. He is Dr. Bhasker Gupta. I welcome you, sir. So let me introduce him. Dr. Bhasker Gupta received BE degree in electronics from Nagpur University in 2000 from Nagpur. He did his ME degree in electronics and communication with distinction from UIT Punjab University, Chandigarh in the year of 2007 and PhD degree from JP University of Information Technology in the year of 2013. He worked with reputed colleges and universities like Thapar University, JP University, and many more. He has more than 16 years of teaching experience at various positions. Currently, he is Associate Professor in Chandigarh College of Engineering and Technology. His research areas include space-time, frequency coding of MIMO wireless systems, pre-coding and receiver designing of MIMO, OFDM system and its implementation using embedded systems. He has 35 publications to his credit, which include book, SCI journals, and IEEE conferences, etc. So with these words, I would like to invite Dr. Bhasker Gupta and request him to kindly enrich our participants with his knowledge. So I welcome you, sir.
Okay, thanks, ma'am, for introduction. I start with the starting of parallel processing. Nowadays, we start everything, and earlier it is the serial communication. Now we always prefer to use the parallel processing to get faster rate, faster communication, or you can say the faster processing of the signals. So in the era of parallel processing or the parallel processor, so we start with the MIPS, and it's basically, we call it as the RISC processor, that the reduced instruction set computers. We know instruction set, we have complex instruction set and the reduced instruction set. So we prefer to use the reduced instruction set computers because it will reduce our complexity but it will increase our speed also. So let me introduce first, but the parallel processing starts with the MIPS one, and the MIPS is the start of the parallel processing era, you can say. So the MIPS, basically its name of the company initially, it's called the microprocessor without interlocked pipeline stages. Actually, in the MIPS, whatever the parallel processing we have, it is done with the pipeline architecture, and later on slides we'll see what this pipeline structure is, or the architecture is. And we have some instructions architecture developed by the MIPS technology, is the name of the company actually. And MIPS is obviously, it's a simple, elegant, and widely used in embedded system nowadays. So benefits, what is the benefit in that? That we have in the later on session discuss the multiprocessors also. So we'll see that what is the benefit of that. Actually, whatever the registers we have, whatever the RAMs, it's all everything is on board. So it's easy to process, you can say. So there are a number of variants in the MIPS. When we start with we call it as MIPS family tree, because there are a number of actually MIPS are characterized into two types: 32-bit and 64-bit. There are various stages in it. So earlier it's long as MIPS 1, as you can see that I just seen the table here. So MIPS 1, 2, then it starts with then there comes the 64-bit processor, MIPS 3, 4. Then the latest release 1, release 2. So they basically characterize. Later on, we will see what are the differences or what are the modernization we done in these processors. In the release 1, release 2, we have the concept of co-processors, which is it's not there in the earlier versions. So now, what are the main parts of the processor? We till now we know these things. I just want to touch on those things and how they are organized in MIPS processor, you can say. So the processor consists of obviously ALU as a arithmetical logical unit, some PC program counter, some register file, and some RAM memory. So the major task is how to put them together so that we can do the parallel processing. Then how to make them execute an instruction as we need. So we start with its parts one by one. We start with ALU first. Now ALU, we obviously know it's a arithmetical and logical unit. It's basically used to do the arithmetical logical functions as required. So the basic numbers diagram shows its internal architecture. Basically, it consists of some gates combination and or gates combination along with mux inverter. So means there's some control signals are there. We have you can say there are two inputs, A and B, and we are with output can be it can be output can be collected to a result. Then obviously if you let's say you add 32 bits, then it maybe carry over there, then maybe overflow flag means it's a basic parts of any ALU design. All right, so then we have what are the different how the registers are organized in MIPS. Basically, register is some chip, so in which we have read register 1, read register 2. There are various pins available over there. So we have a write register and then write data. Then we can collect the read data and read data too. So basically, there are some control signals are there. Like you can say in the diagram or in the pin diagram, you can say. So we have memory request register 1, read register 1, read register 2. These are actually 5 bits. Means in the next slides we will see that how these registers are organized. And basically, it's a 32 register there in total, and they are of 32-bit. Means each register is of 32-bit, and there are 32 such registers are there. Then to address those 32 bits, we need 5 bits. 2 raised to 5 is 32. So that's why this memory register 1 and read register 2, they are of 5 bits. Means they are used to address one particular set of register. All right. So means using read register 1, read register 2, we can using these combinations, you can read the contents of a particular register. Then the write register is again a 5-bit, so it is used to write the register. Right, means it will this combination of bits, it will indicates one register which is in which you can write your result. Then we have data input. So if write, then what the data you want to write to, that will be available on the data input. Then we have request write, means you have to decide whether you want to write it or not. So using this pin. Okay, so here you can see the how these registers are organized. Okay, so as I already told, there are total 32-bit general purpose registers are there. Okay, so basically we can say in the CPU registers we have some general purpose registers and some special purpose registers are there. So there are 32-bit 32-bit registers, general purpose registers. So basically means each register is of 32-bit, and there are two pair of special registers, which is called hold the result of integer multiple and divide, multiple and cumulate instructions. It's designated as high and low. So it means these two special registers, they are used to store the intermediate result of, say, multiply, of division. Like when you divide something by some x, if you divide some y by x, then you have remainder and quotient. So quotient will remain in LO, that's low, and your remainder will remain in high. Similarly with the multiply, when you multiply two numbers, so the low part will remain in low register and high part will remain in high registers. Okay, so they are basically high and low, they are special registers, special purpose registers, which are meant for to store the result of your multiply and divisions. Then we have program counter. Program counter says from earlier terminology, we know the function of the program counter. It stores the address of the next instruction that we want to execute. Okay, so program again special registers. We have program counter, then multiply and divide together, then again low, so which will store the intermediate results of multiply and divide. Now, what about the general purpose registers? As I said, there are 32 in number. So out of that, R0, that is the first one register, is hardware to 0, means anything. It's already connected to the 0. Sometimes, now what is the basic use of that? So it is basically a target register. Okay, so means sometimes we want to discard the output, so that you can do it using the R0. And but the R0 can be also used as a source. So suppose somewhere in some operations or in some arithmetic operation you want to add 0 or something like that. So at that moment you can use your R0. Similarly, R31, it's a destination register. Its default destination registers will be these commands. Later on slides, we will see what is the meaning of these commands. Okay, so whatever will be the result of these commands, so that is by default it stores in R31. You can change that. So means otherwise by default it is stored in R31. Okay, so the remaining register they are used for general purpose use. So here is list of all those 32-bit general purpose registers. What are they used? So as I said, one is constant 0. It's used. It is R0 I'm talking about. Then your there are temporary registers. This is your temporary register used for micro expansion by assembler. Then you have two set of registers which function return values are used for the expression valuation. Then we have function arguments, 4 registers for function arguments. Then these are some temporary registers used to perform that operations, arithmetic operations, but they are not preserved. Okay, so then again a set of temporary registers, but their values are preserved. Now, it depends upon your need of your application. Then we have 4 types of pointers: global pointer, stack pointer, frame pointer, and return address. Okay, so now how to write a register? Basically, there are, every register is associated with two signals. One is your load and store. So if you want to load it, then obviously it should be 1. If it is, you can set it using the instructions. In the later slide, we'll see how to make it 1. Okay, so if it is 1, only then the data will be set or write. Otherwise, you can't write into this register. Okay, so then come to the memory. Then this is the RAM example. So again, some address is there. So address is obviously it is the address of some memory location, means from which you want to read some data to which you want to write, something like that. Then you have chip select. So these are control signals basically. Chip select means if it is 1, then only that chip is enabled. Otherwise, you can't make out of it. The RAM will not work. It should be 1. Chip select should be 1. Then output enable means if you want to extract some output from this RAM, then obviously it should be 1. Then we have write enable. So again, these are actually control signals are there. So write enable means whether you want to read it or you want to write. It should be, then you have data in means if you want to write, then the data will data which you want to write is available on the in. Which one? The MIPS, it's of both types, means it's 32-bit is also there, 64-bit is also there. It depends. Now this RAM is example is showing of 32 bits. It can use 60. Later on, nowadays it should be, yeah, yeah. Actually, there are various variants as I shown in my starting slide. It is basically it starts from 16-bit, then 32, then 64. Now we have various releases are also there. In the starting, I shown that slide. I come to that in the later slides, because these pointers basically like we have program counter and stack counter, so it's basically meaning same as we done in the microprocessor units, right? Like program counter, we know it stores some address of the next instruction that you want to execute. Similarly, with the means some part on the memory tag as a stack. So to point that stack, we have a stack pointer. Similarly, we have frames, means we have set of frames over there. So when you want to point that, means if you want to go to that particular location, so the frame pointer is there. Okay. So then we come to this pipeline architecture. So how they are executed actually. So basically, pipeline, as we know, it's basically a parallel kind, means earlier it's not there. It starts from the MIPS only. Okay, so it is basically divided into the following discrete parts. There are 4 such parts are there. Then these parts are fetch, arithmetic operation, then some memory access, then some write back. So we'll see what is the meaning of this. So fetch means, as we know the meaning, the fetch the instructions from the cache memory and use it in the instruction register and increment the program counter by 4. Now, actually, what is the meaning of this? we know every instruction has some opcode is there. For every instruction it's already existing database for this MEMS processor, you can say. So those opcodes we have to fetch those from that memory, and that will be stored in the instruction register. Now at that same moment we have to update the program counter, because we want to see that what will be the next instructions incoming. Okay, so then comes your register file. Then obviously there are two, like you want to add two registers, the contents of those. So those registers you have to specify. As I said, it's 32-bit there. So there I'm showing you in the latest slide version instruction formats. From those 4 or 5 bits, you can address any of these registers. So there are two sources. One is RS and RT. And now suppose if it now there is one difference. If there is a branch instruction, okay, then we have to load PC with the branch target address. Obviously means when you have branch and jump instructions, we have to jump to some location. So that address should be there in your PC. Okay, so it performs. Then comes your ALU. So it performs arithmetic and logical functions. So this process I'm showing in this diagram. If you see, we have instruction cache over there. So from the cache, the opcode is going to the IA instruction register. From that we have this register file. So from that register file will read RS and RT. Then it goes to the ALU unit, so which will perform the operation which you want. Okay, then you can say in the fourth point that if it is the instruction is load, then you read from the, then we have the data cache over there. You see from this diagram. After ALU perform the arithmetical logical function, whatever you decide, whatever the opcode says. Okay, so the result, it will be either going to the data cache, or it will return to the register. It depends. It depends on the opcode that you are supplied to it. Okay, so if you want to write back to the register, so some R of D is there. That's called a destination register. So again, that have to be specified using those 5 bits. Okay, so either will be written in the memory, that's data in is there, or it will go right back to the buffers and it goes right back to the RD. You can see in the register file RD is mentioned. So it will either, that's why the last step is write back. Okay, means either you want to write the result into some register or to some memory, depends on your opcode where you want to write it. So basically now there are 4 steps in any instruction execution. It's basically in the MIPS processor. It varies actually from the processor to processor, particularly if you talk about the MIPS. So there are four such parts are there, or stages you can say. So fetch, then ALU, then write to the memory, then you have write back. So write is write back over here. Okay, so now there how these pipelines are executed. So there are different ways, different hardware ways, you can say. So the first one, you can say there are 4 clock cycles. So in first clock, or you can say cycle 1, you can call it as a clock or cycle. Okay, so cycle 1 we have fetch, then ALU, then memory, right. So after these 4 stages, the instruction will be completed. Then thereafter again the next instruction start from fetch, ALU, and this. Here you can see that one instruction, to complete one instruction, so the 4 clock cycles are consumed. Okay, so which is you can say it's not it's used in the earlier MIPS processor, the MIPS 16, but it's not used nowadays. So what is this variance? Now you can see the difference. Now we have the 4 pipelines. Okay, so there is one issued after every clock pulse. So this is what the parallel processing is. Means in cycle 1 we start with fetch, then in the clock 2 we start with the first instruction, it goes with the ALU. The next instruction immediately start with the fetch. So means when you go on progresses through this, like you can see in the clock 4 case, so there are 4 things are simultaneously going on. So that's what 4 things in parallel, that's what the parallel processing is. So if you compare it with this earlier one, so you can easily say here, so obviously this one will be better than the 4 pipelines. And if you say how much faster it will be, so obviously if you compare these two, here the next instruction enters in 5th clock cycle, so here it in the 6th. So if you compare this, obviously it becomes 4 times faster than this earlier architecture. So further we have super pipeline kind of things. You can see super pipeline. Now here, so what I did over here, Now, like clock, we know it's positive and negative, some negative cycles. So in the positive, again we fetch some instructions. Okay, then in the negative part we fetch some another instructions. So it's bit seems to be very complex. Yeah, it is complex, but yeah, the processing will be quite faster. And if you compare the earlier pipeline stages, 8 times faster. Okay, so like this, you can manage or you can organize this pipeline structure. We call it as a pipeline. Okay. Now, obviously, then there are some challenges or some hazards in implementing such pipeline structures. One is basically that there are many types of hazards, but usually we characterize in two types. So there's one is your data hazards, and another one is your control hazards. So we call it as there are two types of data hazards. We call a problem type A and B, right? So what it will be? So like we have some three instructions, some x and x y z instructions, and let's say y and z, the instructions are such that your y and z needs and it depends on x, on the result of x. So obviously now if there is a pipeline structure, then means X is in the pipeline, then the next clock cycle Y is pipeline, in the next clock cycle Z is pipeline. If some delay is there, then obviously you can't say, you can't judge the status of Y and Z because it depends upon X. Okay, so these are means at that time your it will not work accordingly whatever as you desire it. Okay, so for the switch over, it means it should be hardwired, right? But it's not. Again, if you hardwired means you are fixing the things. So this is one of the solutions. Then the problem type B means, again I said it's a delayed load, like you are loading from a memory instruction, and let's say from X then followed by Y, that require that means you are loading some value for X, and that value is needed for by Y. Then again there's some delays there. Okay, so similarly, actually this problem comes during your branch and jump instructions. So when you are executing those, you have to be a bit careful. Means similarly, like control hazards, you can say this branch and jump instruction as I talk about. So it will take effect. So what will happen over there means you are branching to some address. Then the next instruction is called the delay slot. So means if you are jumping to some particular address, then after that branch, there is one instruction, whatever it may be, we call it the delay slots. So obviously, if you put that put some another instruction in that, then it may lead to your control hazards. So basically, either we in that delay slot we kept as no operation, either it will be no operation or some updating things should be there. So we want to put an instruction in that. We come to that in the incoming slides on those instructions. Okay, so come to let's say instruction set, that the risk instruction set of the MIPS, and basically they are characterized into 5 different types. We call as load and store instructions. Then we have computation instructions, then jump and branch instruction, then some miscellaneous, then some co-processor instructions. Earlier those co-processors are not there, but nowadays in your release 1 and 2, the concept of co-processor is there. We'll come to that one by one. So we start with load and store. So in the load and store architecture, all operations are performed on operands, obviously, and it's held in processor registers. And main memory is accessed only through load and store instruction. Means if you want to read something, you can use your load instruction. If you want to write something, then you can use the store instructions. So types of loads and store instructions. Okay. So now there are 3 different data types. You can see you can deal with bytes, you can deal with word. Word is further, you can say half word, double word, like that. Means there are instructions for each data type. Okay, if I say LB, it's load byte. If I say LW, it's load word. Okay, similarly a store word. So we'll come to those details. Then there are different types. Okay, so transferring variable size field, first case. Then we have trading transfer data you have signed or unsigned. So signed and unsigned, I think you're aware of. So U stands for, if you are putting U over there, LSU, so it's Harvard unsigned. Okay, similarly assessing some unlined field. Okay, so then we are selecting the addressing mode. Then third is memory update. So it is a detail of. I'm just putting the names over there. Okay, like we have some LB load white, then you have load white unsigned. Okay, then you have load half word. So H stands for your half word. Okay, so then load Harvard, then unsigned, then your load value. Then similarly, we have some aligned CPU load and store instructions, right? So we have store white, store Harvard, store word. Then we have some aligned CPU. Now, aligned CPU instructions, like we have some low store left, okay, then low store right, then you can say low store word left, store word right, like that. So similarly, you can see here, so for the memory update, it's actually memory update is necessary. We will come to that. Actually, when you have different pipeline structures, then there is a problem with the coherence, or there should be synchronized. So at that time means we have number of processors, and every processor is found to write some data over there to some particular memory location. So at that time there is a problem, means if there are two or three writes over there, so which one we should we succeed? Because so at that time this instruction comes, means we have to update accordingly. So there are different structure, means how we write in the programming part. So it's a syntax, you can say. So load some SRT, some offset value of RS. So opcode is of 6 bits, RS is of 5 bits, R of T is of 5 bits, then offset is 16 bits. Okay, so means this offset and the value of this RS, so they will decide the effective address. Okay, so they will so we need to compute this memory address by adding this beer sister to this assigned 16-bit offset. Okay, then accordingly, so it means total again this instruction is of 32 bits. If you add them, so it's again this every instruction is of 32 bit. So now how this let's start a path of load word. So how actually it behaves. So obviously the same structures we need. Well, first it goes to instruction cache. From those we need it, we will fetch its opcodes. Those again both those 4 steps. Okay, so you have to keep in mind those 4 steps. And it goes to your RAM register. So we continue to read those. RS read register means we read 2 source registers. One is your RS, the contents of RS, then your RT. Okay, so then it goes to the ALU. It performs your arithmetic operations. Then it will be write back to the RD. Now, what is this signed extent? Actually, it depends. Means we have to fetch the next instruction. So for this thing is used for the signed and unsigned instructions. Similarly, you can say for the store word. Okay, here again this bit change if you see. So it goes to the read case and go right back to the further. Okay, so so that's how your processor behaves. For load word and store word. Then you have computational instructions. Computational means all those arithmetical and logical instructions. So first we see, you can see here there are total 32-bit instruction long. So the proper syntax is, you can see we have bits from 26 to 31st bits. It represents your opcode. And the bits from 21st to 25th, it represents it's a 5 bits for RS source register. Then again we have 5 bits from 16 to 20 for RT. So it will specify which 2 source registers. One is your RS and RT. These are 2 source registers. Then R of D is your destination register. It is specified by the bits from 11 to 15. Then we have shifting amount. This SAAMT means shifting amount. Okay, it's gain of 6 to 10. Then we have functions, specified functions. Okay, so this function and function actually earlier these are reserved ones, and but in the release 1 and release 2 now we are assigning some functions, different types that we come to later on. Right, so this is the instruction path again. So it's very much means same. Okay, so we'll see what are the different instructions we have. So usually the computational instructions we divide into different kinds. Like we have ALU immediate, so that will deal with the processing of immediate data. Means you have to write the data itself in the instruction. Then the ALU for the two operands, that deals with two operands. Then we have ALU for three operands. Okay. Then you have shift instructions. Again, we have different types of shift, means shift right, shift left, then shift right arithmetic. We will see that in the coming slides. Then we have multiply and divide. So there are totally five types of computation instructions are there. So we start with the ALG immediate instructions. Like we have some add I. So I stands for immediate over here. So add immediate word. So by default it will process your word data. Okay. So that means it should not be byte. Otherwise you have to specify byte. So by default it goes for the word. So add immediate word. Then add immediate unsigned. If you as I told you earlier, that's use stands for unsigned over here. So add immediate unsigned word. Then we have add end your immediate, then load upper immediate, then we have or instructions or immediate, then you can say set or less than immediate. So basically sometimes we need the programming part. Programming I'm not showing over here. So then you can easily understood what is the meaning of this set on less or set on less than the immediate unsigned, right? Then we have switch over. Then there are three operands, ALG three operand instructions. We have simple add. Now we are not putting our I over here, so it's simply add. So it will add words. So those two words we require. So one is for one operand, you can say for two registers, and third one for the destination registers. Then we have add unsigned word. Then the three operand instructions continues. We have some logical instructions now. Means, we have AND gate, AND, then we have NOR, then we have OR, then you have set on or less than. Okay, then you can set on less than unsigned. Then we have a subtract word. Then accordingly we have subtract unsigned. And you can see, well, I'm just putting the list of these instructions. So name clear itself. What is the meaning of this mornings? This two words, so it will count the leading ones. So CLO means count leading ones in a word, and then the count leading zeros in a particular words.
So add immediate is going to add the contents of each.
Which one?
Add immediate.
Add immediate, you have to actually we have to see, one is your opcode, then another one is your destination, the source register, and one is your data that you have to mention over there. So it will add those two contents, and in the storage part, either you can store in the memory, depends on the opcode that you are fetching, or you can store in the RD registers. But
yeah. Add immediate. In other process, it adds that data with the contents of the
immediate means just you have to mention the data itself by which you want to add. Means it's a direct data. Means if you add something that, let's say some 4 plus 5, then you have to mention that data itself which you want to add. The meaning of immediate is that much only. But if you don't want to mention,
do it through some register.
Yeah. Otherwise you can do it from the register. There are three types basically. Means either you can put the immediate data which you want to add, or either you can read that data from some registers, or third is you can read that data from some memory. Okay, so there are three different kinds that you can do. It depends upon.
If I had at 3 and 4.
3
and 4. 3
immediate data.
Yeah, 3 plus 4. And that data has to be in memory.
Yeah, you can put in the registers itself. It's not necessary that it should be in the memory. You can.
Okay, if that is in some register. In some register.
You have to read the contents of first. You have to read the contents of that. But
where I have to read the contents to which register.
You have to mention, like we have 32 registers. Okay. We have 32 registers. So you must know that where your contents are out of those 32. So we will access those with the help of those 5 bits. So 2 raised to 5, so there are total 32 registers are there, right? So you have to mention using those. These are actually basically indirectly you can say these are address lines for that particular registers.
That's correct. For example, if it is R1 and R2, the data is stored in R1 and R2. and I want to add the content.
Yeah, then I shown you can see here, if I go to the back slide, yeah, like this. So here I have to mention that address R1 and R2 address. So then it automatically picks the contents from that, then immediate add. So the opcode will be for the add. Okay.
In opcode part, I will write ADDI.
The opcode of that. Then
I know that opcode of that.
yeah.
Then I have to mention RS is source system.
Yeah. Yeah. So if you are accessing, let's say,
for example, R1.
yeah, then
what is RT?
RT is a second source register.
Okay, R2. Then it is
RS and RT both are source registers, and R and D, RD is your destination registers.
Okay, that means 7 will be stored in RD.
Yeah, yeah. But means now out of now RD is, you can say, it's a destination register. So which register you are specifying as destination register, it's your choice. You have to mention using this 5-bit field.
For example, I will write add R1, R2, and R3. So your 7 will be loaded in R3.
Yeah.
What is that SHAM?
This is a shifting mount. Actually, it's as I told now, that in your earlier processor, these are the by default they are zeros, means there is no of that. But in your incoming releases, shift mount means like if you want to shift some data, like if you remember, shift registers, it basically works as a shift register in that case in the later releases. And earlier there is nothing to do with the add instructions. By default we kept as 0. You can just you can say it is for your future use. Earlier it's kept as all zeros. Huh? Function is again, it specifies, means you want, like in the shift case, you want to shift right. Shift amount, it gives you the amount of shift, means by how much bits you want to shift. Then function means you want to shift right, left, or arithmetical logic. That is your function.
Okay. Addition and all that things, that those bits should be
0. By default it should be 0, means no function at all, right? So we are, I think, at this logical instructions. So again, we have logical gates, then we have AND, XOR, OR, then we have set or less than we have subtract word, exclusive OR. Yeah, here we are. Then we have count leading ones in word. Actually, sometimes it depends upon the programming now. Sometimes we need where this CLO and CLZ are used. When you are for the communications, like this is one of the examples, means it's not key, it's always using that communication. Like if you use you heard about the even parity or odd parity, right? So those algos you can implement using this. Means if I count number of ones, then if it is odd, then you can say odd parity. If it is 1, you can say even parity. Means so this is one of the applications. So now it depends. You can use in the other applications also. So it's count leading ones in word, and then the count leading zeros in the word. Then we have shift instructions. That again we have rotate word right. So ROTR, rotate right. Then we have rotate word right. As I said, by default it works on word type. Then we have rotate word right variable. Now means variable in the variable stands for means you have to mention how many positions you want, right? Then we have shift word left logical. Now if you remember, if you're done with the 885 and 8886, we know that shifting can be a logical, it can be arithmetic. So same here, the way of writing is different, right? So shift word left logical variable, then shift word right arithmetic. Now there are two types of shifting, arithmetic and logical. Similarly, we have shift word right arithmetical variable, right? Then shift word right logical, shift word right logical variable. So the logic and shift instruction usually actually if you say the MIPS, we characterize three broad category. You can say one is the R type instructions, one is called I type instructions, one is called the J type instructions. So this all load and store shifting that comes under your R type instructions. And wherever the immediate data we have to deal, the immediate word, it can be your multiply, it can be your add, it can be your subtract, anything. So that comes your I type. I stands for your immediate. Then your J type. So J stands for your jump. Means basically they are broad categories. So they are further subdivided into arithmetical, then computational, like that. Okay. So basically, the three types are I and J. So the Simpson instructions, then that's your multiply and divide. So we already discussed that to store, usually multiply and divide, then we have multiply, accumulate, then we have multiply. I mean, there are three types basically. One is your normal multiply, which requires a full bit product. Okay, means if you add, then obviously if you multiply the two numbers, then it will full bit, means it will be the double the twice the bits of the operands. So then your low part is stored in your LO register that we already mentioned when I start with the these are special registers, if I already mentioned in the earlier slides. Okay, so low part is loaded in the LO and high part is loaded in the high registers. So similarly, we have multiply, add, multiply, and subtract instructions. Similarly, we have your in case of a divide. So here gives you the list of multiply and divide instructions. We have by default, as I said earlier, also it deals with your word. So divide word, divide unsigned word. Then you have multiply and add word. Then we have multiply and add word unsigned. Then we have now, as I said, high and low, they are special registers. So if you want to read its contents, you can write its contents. You means you can store it, you can move it. Means depends on a section. Like we have move from MFHI, so move from HI. Now where should we move now? So it depends whether, again, there are two options, means registers and your memory. Similarly, you have move from LO. Okay, then we have multiply and subtract word, and then multiply and subtract word unsigned. Then I have now move to. Earlier we have moved from, now we have moved to. Okay, so move to HI, move to LO. So it basically reads contents, write contents, you can say. Then we have multiply word to some register. Okay, so then multiply some word, MLT. Then we can say multiply unsigned word. Now the most important, as I said, J type instruction, or you can say jump and branch instructions. So now jump, basically, as we know that we have in the jump instruction, we have to mention the address where which I want to jump, and then the return address means I have to came back. So again, as we done in the 885 and 886 and later on processors, means it may be unconditional jump, right? So it may be conditional jump depending upon some conditions, right? Then we have absolute, means they are further subdivided. Jump and branch instruction are further subdivided. Then we have absolute unconditional jump. So then we have set of procedure calls, means we have to return back. Then you have to link those addresses. So we call them as a link address in a general register. So first we see the unconditional jump. So actually, in the unconditional jump, the area is specified. We have like in the MIPS 16 and the earlier one. You can see here I mentioned in the processors also on the extreme right. So it can be a MIPS 16 or MIPS 32. So means 256 MB memory is fixed. So we have to jump unconditionally in that area only. Means there is fixed slot. You can say it can be behaved as a stack memory. You can call it as a stack memory. So means we can jump only on the memory locations of particular that area only 256 MB. So only J is the unconditional jump. Means whenever it may be. So wherever it's J, it immediately jump to that particular location. Location you have to specify in that particular area. All right. So then we have jump and link. So link means you have to return back. We have to link address actually. Okay, that's why the word link is. Means we have to came back. Then jump and link exchange, GLX. So jump and link exchange. Actually earlier it is not there, but in the MIPS list 3, this instruction is executed or made public. Then we have unconditional jump using the absolute address. So here we are discussing the unconditional jump. Then in the next slide we will see the conditional jump instructions. So unconditional jump using absolute address. So there is a JALR. There is a jump and link register. Now when you can when you link, so you can link some address or you can link some register. Depends on the instructions. Okay, then jump and link register with the hazard barrier. Means hazard barrier means just it's again a control signal. As I said, there are two types of hazards. We already discussed data and control hazards. So at that time, I mentioned in the control hazards that there is a problem with your branch and jump. Means there is a delay slot is there. So obviously we avoid to write anything in the delay slot. We keep it as an operation so that synchronization will remain as it. Otherwise, once your process is unsynchronized, then you may not get result as you desired, or it will be misinterpreted, you can say. Okay, so then we have jump to some register, then jump register with some again hazards barrier. Then related to PC related to conditional branch instructions. Okay, so then we have now we discussed earlier the jump and on the branch instructions. Okay, so branch on equal. So equal means it will check the contents. We have to specify those two. It can be two memory locations, contents of those memory locations, or it can be two registers. So it will branch if it both are equal. Then, or as you can say, the branch if they are not equal. Right, the condition is there. That's why it's called a conditional branch instructions. Absolute address, again you have to calculate. Means like we have there are two types of address, if I mention, I think so. Yeah, okay, I think it's not mentioned. So there are two types of address. One is your absolute and relative address. So I think we done in 86. That means one, it depends on your addressing mode. Addressing mode I just skipped in the slides. I'm not repeating it. So it's literally writing your address modes. That it can be your immediate, it can be your relative, it can be your absolute. Right? It's way of calculating those where you want to jump to. Okay.
How do we calculate the actual address?
Absolute address, I think if you can see from 85 knowledge and 86 relative, how you calculate relative. So like in the absolute and relative, we have absolute means you have to directly mention the contents. Means like if you remember in the 86 we have some contents of some register. Then we there are two types of addresses. Like one is your logical address, one is your physical address. Okay. So how you translate logical to address means we have some address stored in the memory, then we add some offset, that it becomes your physical address. So that is your relative address, right? Absolute means you have to, that contains the initial logical address is again some defined value or defined address value. So you can add those and then it comes to the absolute. It means absolute and relative means these are the ways to calculate a particular addressing mode. Okay, so addressing mode that I'm
some offset to the value of program counter.
no, program counter is different. Program counter is different. If I go yes.
In 8051 or some other thing, there you have long jump and short jump.
Yeah.
Isn't it?
Yeah.
Short jump is your absolute address. There's the address.
No, how
and we calculate the actual address by adding that offset to the contents of program counter.
right.
To whom we are adding that address?
Now in here the offset, now it depends that you are writing, now you're getting that offset from some memory or some address. If you see the instruction I shown in the earlier slides, the offset address is directly written over there. Then we are adding those offset with the RFS, right? So RFS, those contents, they are used to access some address of the particular memory location. Okay, so those contents, now the PC is different. PC, it will store the address for the next instance. It will be automatically updated. If you in the earlier slides, I shown that the PC is incremented by 4. Okay, so it will store the it will not related to the address which you are storing your data. Okay, so PC will contain the address of the next instruction. It will contain the address where your next instruction you want to fetch. Okay, so PC will not contain the address at which you want to store the result or store the result of any arithmetical logical operations. So that's why this PC is mentioned as special address. Means it basically you can say user can read those addresses and accordingly it will be updated.
So what is the advantage of address? Yes,
What is the advantage of?
absolute address.
It's again, as I told, na, absolute address is just to mention the address where you want to store the data, or whether you like in the jump instruction, right? Here, in the like instruction J, so where you want to jump, nothing is mentioned over there. So that is the absolute address. Means you have to mention the address over there. Means it's direct address. You need to no need to calculate. Okay, like in the other cases, in the relative address, you have to calculate the address by adding the offset plus the contents of the registers.
All the instructions are 4 byte.
4 byte.
Right.
Yeah.
All the instructions are 4 byte. The thing is that long jump and short jump. Long jump is 3 byte and short.
See, long jump and short jump is not there in.
That there. Absolute addressing. Why we do it? Because that instruction size is small. But here instructions
Yeah,
are
same,
4 byte.
same. No. You can see over here, it's jump is only in the 256 MB, so it's a short jump only. You can correlate such several instructions that these are short jump instructions. So same concept. Nothing is changed. Nothing is changed, right? In the 8051, like we have short jump, here we have this unconditional jump, but we are fixing the memory size. So this is a kind of short jump only. So the concept of absolute address will remain as it is intact. So nothing is changed. As you understood in the short jump, the concept of absolute address in the short jump, same concept applies over here. Here we are fixing the memory size that it will go on 256 MB only. All right. So then we have conditional branch. So branch on greater than or equal to 0, right? So BGEZ. So branch on greater than or equal to 0, then branch on greater than or equal to 0, and link. So wherever you have to link means you have to link the return address, right? So then branch on greater than 0, branch or less than or equal to 0, then we have branch on less than 0, branch or less than 0, and link. Yeah, then branch on equal likely. Now branch on equal likely. Now what stands for likely means like you have the options over there. Actually, again, option in a sense means you can still change the address. So that's why it's equally likely. Otherwise, in earlier instruction you can't. Even in the 85 and 86 you can't. Okay. So branch on equal likely, then branch on equal then or equal to 0 and link likely. Okay, likely, as you understand, same thing means it can be like, or means you can or you can't be, means you can change that. So branch on greater than or equal to 0 likely. So similarly you have branch on less than or equal to 0 likely. So means the various variants of that branch instructions, right? Now, as we discussed so many times, there is a delay slot, so we have to bit careful in using a jump and delays, jump and branch instructions. So the instruction immediately following a branch is said to be a branch delay slot, right? So if you put some another branch or a jump instruction in that particular slot, then the operations of both instructions are unpredictable. Means you can't, the processor will now you have to prioritize. If you know about the interrupts and unconditional interrupt, conditional interrupts, traps or interrupts, then you have to prioritize using those interrupts. At which one you proceed first. Otherwise, your results will be unpredictable. That's why in the delay slot we usually prefer to kept it in operation. Okay. Then we have miscellaneous instructions. So it's for the serialization. There are again 5 types. So basically, it's not you can say it's not a part of some programs. Basically, it's used for the special purposes, right? So we have 5 types. Instruction serialization. So as the name understood, used to the sync. Okay. Then we have sanctional instructions, conditional move instructions, prefetch, and operations. So there's a list of that. So you can say it's again the trap and interrupts kind of instructions. Again, some equally likely and trap if greater than or equal. So they're again conditional trap instructions. Okay. So basically they are combined with jump and branch instructions, right? Then we have some move conditional. Okay. Then have a move conditional if not 0, move conditional or floating point 0, move conditional on 0. Then we have prefetch instructions, right? Then we have NOP operations. So NOP, as I said, means during that delay slot we have to put this NOP instruction accordingly, right? Now this is a co-processor. Now if you say in the MIPS processor, earlier this co-processor concept is not there, but in the later releases we have co-processors. Means we have 4 types of processors. See, that's designated as CP0, 1, 2, 3. So we are fixing that actually. It means in the latest release, that's a release 3, we have 4 co-processors, right? So the functionality, so coprocessor as the name suggests, it's working with in parallel, you can say. Again, a parallel structure it follows. So CP0 is incorporated in the CPU chip, and it supports the virtual memory space and exception handling. That means those are exception instructions. And it's also referred to as system control coprocessor. Okay, it will translate. So what is the function of CPU? Now CPU0 is fixed one, kind of fixed operation is there. It's designated to translate the virtual address into the physical addresses, then manage exceptions, handle switches between your kernel, supervisor, and user states. Means is basically the CPU is used for the control processor, you can say. Then CPU1, it is reserved for the floating point coprocessor. Now it's called FPU. In the earlier versions of MIPS, there is only fixed point arithmetic. Okay, so what in the latest releases we have both fixed and floating point arithmetic. Means whatever the set of instructions we discussed till now for the there's for the fixed ones. Okay, so similarly we have instruction set for the floating point. Same set of instructions. Obviously, change in syntax, change in meaning is remain same, and also lot more additional instructions are there. Okay, so CP1 it's reserved for the floating point coprocessor, and CP2 is available for some specific implementation. Means it's just like it works as microcontroller. Like microcontroller, we know what is the difference between microcontroller and controller is that it's meant for some specific purpose. So same thing you can do with the CPU. CP3, it is reserved for floating point unit in release 1. Then it goes in the MIPS 64 architecture as well as in the release 2 implementation of that. Means this CP1 and CP3 both are meant for this floating point arithmetic. Okay, CP0 for the control purpose, CP2 is for the your work as microcontroller kind of thing. So instructions. So again, LAXZ. Now this the suffix is Z in a suffix. So it represents which coprocessor you want to deal with. So it can be 1 or 2, right? Otherwise, CP0, as I mentioned, is for the control purpose. Okay. So load double word to that particular coprocessor, which is indexed by Z. Okay. Then load word to that coprocessor. Then store you can store double word to that and store word from that. Now fixed point we already discussed. Floating point, there's generally 3 types of floating point sports. It's, you can say, floating type S, that is a single, or then you have PS paired single. Then you have 64 bits. So there are 3 types of floating point arithmetic sports. When you S, PS, and D. Okay, so dot FMT U extension, like we have extension of FD data file. So even in the FPU data format, that a floating point unit, dot FMT is, whenever in instruction you find dot FMT, means we are talking about the floating points. Okay, so it can be, there are 3 different types. So again, accordingly the instructions will change. Okay, even there are some instructions by which you can convert these data formats into each other, means S to PS, PS to S, then S to D, like that. So we'll quickly look into those instruction set of the FPU. So here I shown the three different FPU formats. We have single precision, this is called S. We have double precision point, that's single precision your S, double precision is your D, then the paired single your PS. So again, we have 32 floating point registers, and every register is 32 bits wide using, and similarly in the 64-bit processor, so this FPU is a 64-bit wide long. So we have 5 FPU control registers which are used to identify and control this FPU unit. Then we have 8 floating point conditional codes. Okay, so that is a part of the control register, FC SP register. Okay, so same thing. So FPU instructions, again, if you see, there are of 6 types. Instruction now I quickly go through because it's about to over. Okay, so FPU instructions, data transfer instructions. Then we have arithmetic instructions. Then conversion. Now it's not there in the fixed point. Okay, data transfer is there in the fixed point also. Arithmetic is there in the fixed point also. Now the conversion is not there. Conversion in the sense, as I told, that there are 3 different floating point formats. So you can convert to one another using these instructions. Then we have formatted operand value move instructions, that way it is there in the fixed point. Then we have conditional branch, then miscellaneous. So data transfer, again, some load word index to floating point, then load double. Now here you can say in the fixed point we are not dealing with the double word, right? But here it is there. So load double word, then double word unsigned to floating point. Then so I think you are aware of this fixed point and floating point arithmetic. So same case here, we have some exponent part, we have some mantissa part, so that you can store in different registers and so. Okay, then load word index to floating point, then store double word index to floating point. Then similarly FPU move instructions, move to and fro, that is you can move the control word. Okay, this facility is not there in the fixed point. You can't you can only access the contents of control word. Okay, but here you can move the control word from floating point, then to floating point, move control word to floating point. Then we have move word from floating point, then we have move word from high part. Okay, then we have arithmetic instructions. So same, now we have to mention .mnt, means we are mentioning the mentioning that it is particularly meant for FPU floating point arithmetic, right? So you can see over here, so floating point absolute right. Okay, then floating point add, then you have floating point add with piercing. Now here we are mentioning PS, means we are mentioning the data format over there. So this instruction add FMT to PS, it will work only on PS kind of FPU. It will not work for S and D. Okay, then we have floating point compare. Okay, floating point compare with the paired right, paired single, and floating point divide, floating point divide and multiply instructions. Then the arithmetic continues. Now here we have floating point reciprocal some instruction, which is so fixed point reciprocal is not there. Okay, so there is some additional facility we have. So in the FPU, along with we have all the facilities of almost all the facilities of fixed point, along with some additional facility, like we have this reciprocal. Okay, floating point reciprocal. Then floating point reciprocal with the square root. So this facility is again not there in the fixed point arithmetic. So floating point arithmetic continues. Then floating point multiply and add. Floating point multiply and add with paired single, right? So then floating point multiply and subtract, means same. The functionality will remain same. Only the way of only you can say syntax got changed. Then that's the conversion part, so which is it's not there. It's in your fixed point. Means we can. There are three types of formats that we already discussed. Okay, so first instruction, it will floating point convert to double positions, that is to D, right? So that format dot fn that you have to mention, like you have CVT stands for convert to. Okay, that's your CVT, and D means convert to D. Okay, similarly we have convert to long action, then you have floating point convert to your pair single, then similarly convert to your single. Okay, SBTS, CBTS, sorry. Then we have floating point convert to single, then we have floating point convert to what axle. So the conversion continues. I can read those. So then if you see, if you are familiar with the MATLAB, so in the MATLAB programming also we have floor and seal instructions. Means so same use, same use is there in your FPU. So it's very unique thing. Means it's not available earlier. Okay, so means floor and seal means just to approximate the thing. So just to particular extracting a particular coordinates of particular chains of gramming. So that is done using floor and seal instructions. So it is there in the FPU. Then format move instructions. So we have floating point to move, then floating point to move paired single. Okay. So these are all instructions which are related to the floating point. Then we have FPU conditional move. Then which is now we are putting the conditions here. Means we are move instruction with the true and false conditions. Like if it is true, then move. Then it is false, then move. In floating point, move conditional if FP true, so it's kind of flag. Okay, working as flag. Then floating point move conditional. Okay, so it's conditional move and now it's conditional on 0 and non-zero. Earlier in the above table, it's FPU conditional for true and false in same case, but it's conditional for 0 and non-zero now. It means conditions are changed. The conditional branch, if you remember, in fixed point we have BEQ and BNEQ. BEQ means branch on equal, right? Here we have branch on false and true. Then we have branch again. Likely concept is also there in the fix. So we have branching if likely. Okay. Then some miscellaneous. Okay. So same means move point upper, then you can say put lower one, then lesser and greater than, same case, same case. So this is all about to the MIPS, and so we discussed that how this pipeline architecture is involved and how it's evolved, and there are various stages and their instruction set. So nowadays, even in my next lecture, we will see that how they are grown up now. MIPS actually it comes in 1980s, I think so. So after that, we have MIPS. Different releases are there, and latest release 3 of 60 comes in the early 2000. So, but now this concept is grown, and now we are using this concept to the multiprocessors, and so that we continue in the next session. Thank you. Any questions if you have?